Okay, this next lesson we'll talk about yield surfaces. And basically what we're going to do is define a surface that's fixed in stress space that defines a yield condition. So to motivate this discussion, let's say that we took that steel bar that we did in section 5.0, and instead of doing a traditional uniaxial tension test, we first apply a big pressure to the steel bar. So we put it in a cell and apply a lot of air pressure to the cell so that we get horizontal and vertical pressure applied to the steel bar first, and then we do the uniaxial tension test. Or alternatively, you could take the steel bar down to the bottom of the ocean where there's water pressure acting all over it, and then you do the uniaxial tension test. Well, we can represent that by this diagram, or this set of two diagrams here. We have an initial condition here, where we just have applied a pressure all around the steel bar, and I'm going to call the pressure sigma 3c, and that's a notation that we'll use in soil mechanics. So the 3 refers to the minor principal stress component, and the c is called consolidation. We'll get into consolidation, but basically when we test soil, sometimes we apply a pressure to the soil first to mimic a condition in the field, and then we do the strength test. So sigma 3c is the minor consolidation stress. Okay, and then we reach a final condition here where we keep the sigma 3c in all directions, but now we've changed the vertical stress to be equal to sigma 3c plus sigma y. Okay, now one of the things to keep in mind is that we're adding tension to the stress that already existed. Okay, we're not starting from 0 anymore like we were before. We're starting from a condition where there's already some stress on the bar, albeit equal in all directions, and we're adding a stress to that. So it's tempting, sometimes students make the mistake of just putting sigma y there on the vertical axis. You have to keep in mind it's sigma 3c plus sigma y. That sigma y is being added to the stress that existed before. All right, now let's talk about the Morse circles. So first, we have the initial condition, and this value is equal to sigma 3c. So let me label that stress value so it's clear. Draw a line here, like that. So initially, we have a more point. Maybe I'll erase this one. So initially, we have this blue circle right there. And since the stress is the same in all directions, there's no diameter to the Morse circle. There's just a point, right? It's an isotropic stress tensor. So we could even draw those stress tensors out. Let's do it. Sigma initial is equal to, we would have sigma 3c, 0, 0, 0, sigma 3c, 0, and then 0, 0, sigma 3c. Right? So the stress is the same in all directions, and there's no shear stress imposed. All right, and then we would have sigma final. I'll put it in green. All right, and in this case, we have sigma 3c plus sigma y. That's the first component. And then we would have 0, 0, and then 0, sigma 3c, 0. It's not a very good 3. Redraw it here. And then we would have 0, 0, sigma 3c. All right, so that's our final stress tensor, and the corresponding Morse circle is this one, right? So we have the sigma 3c is the initial point, and then sigma 3c plus sigma y is the final point. So that's the major principal stress. This is the minor principal stress. And the circle will be the same size as the circle when we tested the specimen in air. All right, you might have been thinking, how on earth is applying pressure to the steel going to change its strength? It turns out it doesn't, right? If you take the steel bar to the bottom of the ocean, you don't make it stronger or weaker. You do the test, it's the same strength. So applying pressure to steel doesn't change its strength. And what that means is that we now have a point right here where the steel bar was yielding if we did the test in air, and then we have another point that's at the same height in tau space if we tested the steel at a high confining pressure. And if we just connect those 2 points together, we get a yield surface, right? So that line right there is in stress space, in tau sigma space in this case, and it marks the yield surface. So what the yield surface means is that if the stress condition results in a Mohr circle that's touching the yield surface, then you are on the yielding part of the stress strain curve. You're no longer on the elastic part. You've now started to accumulate some plastic strain and permanently change the shape of the material. So here's the yield surface. If we have tau versus sigma, now I've drawn these as nice lines instead of hand-drawn lines. There's a yield surface that's positive tau and then a yield surface that's negative tau as well. Okay, so if you took that bar and did compression instead of tension, it would have the same strength in both directions. So, you know, up here I was only drawing half the Mohr circle. The full Mohr circle would actually go whoops, let me try that again. It would actually go tangent to both lines, just like that, right? So that's the actual yield surface. It involves two lines. Okay, so if the Mohr circle touches the yield surface, the material's yielding. We use laboratory tests to measure the yield surface. Okay, what we want to know when we do material characterization is what's the value of this line? In this case, it's very simple. It's just sigma y over 2, right? Or sigma y. You measure sigma y from a uniaxial tension test. Now you know where that surface is, and you can assess whether any complicated field loading condition is going to result in a material failure. Okay, field loading conditions are rarely the same as the laboratory test conditions, but we get the yield parameters from the laboratory test and then assess whether the field loading condition causes a yield criterion to be met. Okay, now, what if we did a more complicated loading condition? Let's say that we had that same material, that steel material, and then we have some kind of initial consolidation test, stress, sigma 3c, and we're adding some axial stress to it, sigma a, but we're also adding shear stress, sigma xz. So, you know, this might happen like if you had a piece of rebar in a concrete beam or something like that, and it's being stretched and sheared at the same time, right? Real beams have shear and they have bending, which causes axial stress, so it's a combined loading condition. All right, well, if we draw the Mohr circle, right, so for the horizontal stress condition here, we have sigma 3c. The shear stress component tends to rotate the block diagram in a counterclockwise direction, so it's positive, so you have that point. And the vertical stress is sigma 3c plus sigma a right there, and then the shear stress tends to rotate the element clockwise, so it's negative, minus sigma z, minus sigma xz. So once we have these 2 points, we can easily sketch our Mohr circle, which is shown there. And what you'll notice is that the diameter of the Mohr circle is, first of all, it's equal to 2 times sigma y over 2. So let me explain first one key concept that I forgot to mention. What I'm assuming is that we're increasing sigma a and sigma xz, and that we've reached a failure condition, right? We're ramping those two things up together, and then eventually the circle will reach failure. That's why I've drawn it as being tangent to the yield surface here. Right? There was a time earlier in the loading sequence where the Mohr circle was maybe like right here, right? And then we added a little more loading and it goes right here. And neither of those circles are yielding. That's in the elastic range. What I'm assuming is that we are yielding. So there's this point of tangency right there. Okay, and then there would be a corresponding negative yield surface that I haven't drawn down there. Maybe I should draw it just for completeness. Let's extend this axis down. And we'll draw another yield surface right here, like that. Okay, so both yield surfaces are in there. All right, now one thing we will notice is that the amount of axial stress that we were able to impose right there is smaller than the diameter of the circle, right? Or the diameter could be measured this way. So what that means is that sigma a is less than sigma y. Okay, sigma y over 2 is the radius, sigma y is the diameter of the Mohr circle. or measured vertically this way. You can see it very clearly, right? This one's positive sigma y over 2. This one is minus sigma y over 2. So that full distance between those two yield surfaces is sigma y. Sigma a is less than that. Okay, that means that if we have this sort of combined shear and tension mechanism acting on steel, the uniaxial stress at failure is less than the yield stress that you measured from your uniaxial tension test in the laboratory. All right, it's often easy to forget that or to ignore it, but it's important not to do it, right? We've got to think of stress in terms of more circles or as a tensor-based quantity. So here we have this conclusion, very important conclusion. Sigma A is smaller than the diameter of the Mohr circle. Therefore, sigma A is less than sigma Y. So you can't think of uniaxial capacity as being fundamentally a material property, right? You have to think of it as defining a yield surface that is fixed for the material, but then any other loading condition can also cause that yield to happen. Now, if we want to solve for how much sigma A is, we can easily do that using trigonometry. So what I'm going to do is copy the circle over here, and then we have this right triangle right in the middle that we're going to look at. So if we bring that right triangle down here and start labeling the different side lengths, we have sigma A over 2 on the bottom, sigma xz on the vertical, and then sigma y over 2 is the hypotenuse. So we can use very simple trigonometry here to define the equation using the Pythagorean theorem, and you find that sigma A is equal to sigma y squared minus 4 sigma xz squared, square root of that quantity, right? So if sigma xz is 0, then sigma A is equal to sigma y. If sigma xz is greater than 0, even if it's negative, it could be positive or negative, it doesn't matter because you're squaring it, then sigma A is less than sigma y. So applying a shear stress reduces the axial stress capacity of the material. And I would argue that maybe you've experienced this before, right? So I always like to tie these concepts into something physical that students can relate to. So let's say that you have a bottle with some kind of beverage in it, and you have a cork in the top of the bottle. You pour yourself a drink, you push the cork back into the bottle, and now it's kind of stuck in there. Well, when you go to take it back out to pour more of that beverage, you could just pull straight up on the cork, right? Like, pull the cork right out of the bottle. Or you could simultaneously pull up on the cork and twist it, right? So you're applying a torque and you're pulling up at the same time. Which approach is easier? I would argue that most of us do the second option here, where we apply torque. And let me explain why we do that. If we can fail the interface in torsion around here first, it makes it much easier to pull the cork out. It reduces the axial stress that we have to apply to that interface in order for the cork to start moving upward. Whereas if we only apply axial force, we have to pull harder, right? Because we have to cause failure around that frictional surface between the cork and the inside of the bottle. So that's kind of a very sort of physically motivated description of how these stresses interact with each other and they couple with each other. And we can handle that coupling very, very easily if we remember that stress is tensor-based. All right, now steel is a pressure-independent material because the yield stress does not depend on confining pressure. So you take the steel bar to the bottom of the ocean, you haven't changed its strength. It's still just as strong as it was in air. But there are other kinds of systems that are pressure dependent. And the simplest one is a sliding block. So imagine that we have this block here and it's resting on top of a rigid surface and there's some vertical force on it, N, and then we're going to impose a horizontal force T that will cause the block to slide along that surface, and then there's mu, the coefficient of friction between the block and the surface. Well, it turns out if N is big, then T required to fail the sliding block is big too. If N is small, T is small, right? So if we try and draw a yield surface now for this material, we end up with an inclined yield surface. It's not constant like it was for steel. It has a slope to it. And another thing I'll point out, I'm actually drawing my yield surface in terms of forces here. This is in terms of torque or horizontal force and normal force. So yield surfaces are most commonly drawn in terms of stress, but you could draw them in terms of force as well. And I could easily, of course, convert to stress quantity just by dividing by the cross-sectional area of that block where it's coming into contact with the rigid surface. So, okay, the sliding block has a pressure-dependent yield surface because the height of the yield surface depends on n, right? So T depends on n, and the slope of that relationship is mu, the coefficient of friction. So we can write an equation representing that yield surface. And, you know, one way to write it is T equals mu times n. More commonly, yield surfaces are written out so that they define some quantity that equals 0. So T minus mu times n equals 0. And what you can do now, if you, let's say you wanted to know if this block was sliding or not, you could measure n, you could measure T, and then if you knew mu, you could compute T minus mu times n. And if this quantity is negative, right, if this is the capacity, this is the demand, if the capacity is bigger than the demand, the yield surface will be negative and it's not yielding. If you've reached yield, the capacity will be equal to the demand and it is yielding, right? So you get 0. You'll never get a positive number here. Okay, you can't put more stress on the material than its yield strength. That just doesn't happen. That's impermissible. So this yield surface equation is always going to be less than or equal to 0. Now let's take that sliding block analogy and extend it to soil. All right. When we have soil, here's a little network of soil particles that are all in contact with each other. And what I've done is impose some confining pressure here, sigma 3c to the soil. And as that confining pressure is imposed, all of these inner particle forces that I've drawn will increase. Right? You get these inner particle forces acting on the soil. And those particles are pushing against each other pretty hard. If you have a big pressure on it, then it takes more shear stress to cause them to slide. So when we fail the soil, we're talking about sliding particles past each other. And maybe they rearrange into a denser configuration or something like that. So the confining pressure increases contact forces. And since soil failure means that those contacts are slipping, it makes the soil stronger because it takes more shear stress to cause the particles to slip. Yield surface looks a lot like the sliding block yield surface. Now I'm plotting tau versus sigma prime, so this is more circle space. And we end up with this blue line for the failure surface. And then, of course, there's a mirrored blue line down here that is also the failure surface. And any more circle that you draw that goes tangent to that surface is going to be at a failure condition, right? And then the slope of that failure surface is the effective friction angle. So the tangent of phi prime, let me make sure that this is an angle and not a slope. I should be more careful about how I draw it. Phi prime is this angle, right? So the tangent of phi prime would be equal to the coefficient of static friction, if you want to think of it that way. But in this class, we'll just define it as an angle itself. And a common friction angle for sand might be 32 degrees, 34 degrees, something like that. So here's the initial condition, then we're adding vertical stress until failure, and it goes tangent to that failure envelope, right? Now the other thing that I'll mention is that the failure surface, these failure surfaces that I drew go through the origin, so they go right through the point 0, 0. What that implies is that the soil falls apart if there's no confining pressure acting on it. So this would be like beach sand. If you go to the beach and scoop up a handful of the dry sand, it just will fall apart and flow through your fingers. But there are other kinds of soil, like cemented sand. So let's say that you have two sand particles that have been in contact for a long time, and then minerals have precipitated out of the water and are cementing these particles together now right here. Well, in that case, if you remove all pressure, the cement is still holding those particles together. And so you get a different failure surface. You get the friction angle prime. I'm cleaning that up and make sure it's an angle. slope. There you go. So the angle's phi prime. And we now have this new parameter here, C, right? And C prime is the cohesion, the effective cohesion that marks how much cement there is bonding these particles together. So anyway, now we have two parameters, C prime and phi prime, that quantify the surface. And if you do have cemented particles, you can actually get tension, right? If sigma prime becomes negative, there's a tension region here, whereas if sigma prime is positive, we're in the compression region. So you might get a Mohr circle that would come down here, right? This would be a failure condition, not a very good one there. So that Mohr circle would involve some tension acting on the soil. And the tension exists because the cement is in there holding the particles together. So you can actually pull on them a little bit before they will break. All right, so that's it.